Let's work through an example calculating the induced electric field. So press pause, see if you can work through this on your own. I think you can, even though it's really, really tricky. At least get half of it, and then press play and we'll go through it together. So I'm going to be calculating my induced electric field. In this case, it's the magnetic field that's changing. The reason that my flux is changing is because my magnetic field is changing. So to calculate how the flux is changing, I'm going to use the version of this equation where the field is the one that's changing, right? We could also have a version where the area is changing or where the angle is changing, but in this case it's the magnetic field because it started off at 1.5 Tesla and it goes to 0 Tesla. So let's figure out how big the rate of change of that magnetic flux is. So I'm calculating dB dt, how fast is my magnetic field changing, what's the rate of change of my magnetic field, and I know that it goes from 1.5 Tesla to 0 Tesla in 20 seconds. So here I'm looking at how my field has changed and how much time does that take, how fast does that happen. So I get negative 0.05 Teslas per second. It's technically negative. I'm just going to calculate magnitudes and then I'll figure out the direction at the end. So I'm going to plug this in here for dB dt, and I can find that the rate of change of my flux is equal to 0.075 times A. Well, A is the area that I'm considering. Here is the loop. This is the loop that I'm going to consider when I do my line integral. So I'm going to take the area of this loop. That's just pi r squared. I drew a loop of radius r. So the area of that loop is pi r squared. This gives me the rate of change of the flux through this loop. I don't have to worry about theta because the magnetic field is perpendicular to the plane of my loop. So that just gives me that my flux is changing at a rate of 0.075 pi r squared through this loop here. Now I can use my equation that relates the change in the magnetic flux to the line integral of the electric field around this loop that I drew. Well, if the electric field is perpendicular to this loop, then that part of this integral would be 0, so I can ignore any of those electric fields. And just consider that there's an electric field in the direction of the loop, and that electric field in the direction of the loop is going to be equal to the rate of change of my magnetic flux. Based on symmetry, I'm going to say the electric field is uniform everywhere along here, so I can pull it out of the integral. So here is my, I've set my rate of change of my magnetic flux equal to my line integral of the electric field. I'm going to say that due to symmetry, the electric field should be have the same value everywhere on this loop. So I pull it out. And now this is just saying take the line integral of your loop, take the length of your loop. Well, that's a circle of radius r, so the length of that circle is just 2 pi r. And then I can solve for E and find that the electric field at a distance r from the center of this region is equal to 0.0375 r. Now let's figure out the direction of the electric field. And the way that I like to figure out the direction is to pretend like there is a wire here and to pretend like there is a current. Because whatever direction the current would be would also be the direction of the electric field because the electric field pushes positive charges in the direction of the field. So I'm going to come back to my picture and I'm going to consider there's a magnetic field going into the page and it's getting smaller. So I need to create a magnetic field that is also into the page to oppose that change or to compensate for that change. So I want a magnetic field going into the screen. And let's again pretend that there's a wire here on that dotted line. Let's look at this bottom segment of the wire. For this bottom segment of the wire, the r hat direction when we're considering inside the loop would be straight up. So I want my fingertips pointing straight up and my palm in the direction we want our magnetic field to be in, which is into the screen. So if you have your fingertips straight up and your palm into the screen, your thumb points to the left. And we were considering this little segment of wire here. That means in this segment of wire, the current would be going to the left. And if we did that for other segments, we would figure out, or just by looking at this, that the current would be going in this direction if there were a wire there and if there were an induced current, it would be going like this, clockwise. There is no wire there, though, so there is no current. What we have is an electric field, but that electric field is in the same direction that that current would be. So we can say that our electric field is tangent to the circle in the clockwise direction. So this is how big the electric field is, and this is the direction of that electric field. And this electric field is being created because our magnetic field is changing. So the changing magnetic field is inducing an electric field.